Hello everybody. Today we will talk about postulates of quantum mechanics. Now, along with postulates of quantum mechanics, I will also describe the direct notation, which is also known as the bracket notation. Postulate 1 of quantum mechanics states that the state of a physical system is characterized by a state vector that belongs to a complex vector space V called the state space of the system. The complex vector space will be called as the state space of the system, and the state will be represented by a state vector, which is basically a ket vector, and I will describe further what is the state vector and how to solve how to represent the quantum state using the state vectors. Now, there are various possibilities in doing the direct notation. Now, the first possibility is only ket notation. So you have a ket. This system that I am trying to describe here is a single qubit system. Either it can be ket 0 or it can be ket 1. So since two states are possible, but it is a single qubit system, two states are possible. So therefore, the dimension of this system will be 2. So it is a two-dimensional system. Now, if you have in this system I am trying to represent here, this is a 2 qubit system, so the dimensionality will be 4 because there are 4 states possible. In the 3 qubit system, the dimensionality will be 8 and so on. Now, ket 0 is represented, ket 0 will be a column vector here. So, ket 0 we can represent to be 1 0. This is the column vector representation of ket 0, and what is the representation of ket 1? It is 0 1. Now, in the case of ket 0 0 in this 2 qubit system, so what is the column vector for this? 1 0 0 0. For ket 0 1, the representation is like this: 0 1 0 0. Only one time 1 will come at the specific position represented by the ket for which we are taking the ket. Similarly, we can write the column vectors for ket 1 0 also and ket 1 1 also. Now, in the case of ket 1 0 1, since it is an 8-dimensional system, so the size of the column vector will be there will be 8 rows and 1 column. So it will be 0 0 0 0 0 and 1 0 0. So this will be the column vector for 1 0 1. And you can also write the column vectors for ket 0 0 0 up to ket 1 1. So there will be 8 states possible. Now, another representation in the direct notation is the bra notation. So what is the relationship between the bra and the ket? So bra is actually the adjoint of ket. So what is the meaning? What is adjoint of the ket here? The adjoint means you have to take the complex conjugate and then transpose it. Like so bra will be a row vector basically. So bra 0, since we have represented here ket 0. So what will be bra 0? Bra 0 will be given by 1 0 here, and what will be bra 1? It will be 0 1. So similarly, we can go for other systems of higher dimensionality. Now let us take an example here. So ket psi is represented by, actually ket in a single qubit system you have ket 0 and ket 1 possible states. These are known as the eigenstates or the computational basis states. Now we can represent the superposition state. Let us say a quantum bit or quantum system, a qubit is represented by alpha ket 0 plus beta ket 1. So using these two computational basis states, and we can represent a quantum state which is in superposition. Now alpha, where alpha and beta, they belong to complex, so they can be complex numbers, right? So this is the qubit given in superposition. Now if I have to find out the bra from here, basically what will be ket psi? So ket psi is, if you represent it in the matrix form, So ket psi is a column vector. It is 3 plus 5 iota and 7. So this is ket psi. I have to obtain bra psi from here. So as I have told you that you have to take the complex, you have to take the adjoint. Adjoint means the complex conjugate. So if you take the complex conjugate of the elements of this column vector, so since 7 is real number, no change. This is 3 plus 5 iota, this will become 3 minus 5 iota, and then you take the transpose. So therefore, bra psi will be equal to 3 minus 5 iota and 7. This will be a row vector. That's the relationship between the ket and the bra. So basically, ket and bra are analogous to the classical world vector algebra. We have a column vector there, we have a row vector there. So column vector is analogous to the ket vector, and the row vector is analogous to the bra vector. And they see column vector and row vector, the two vectors we cannot add, right? So if we cannot add, so therefore they do not belong to the same vector space. Actually, the row vector belongs to the dual space of the column vector. So similarly, here the bra is the bra vector belongs to the dual space of the ket vector, right? So another possibility in the direct representation is the ket notation. So we have two kets here. For example, I have considered ket psi and ket phi. So basically, this will be the tensor product of the two ket vectors, right? And tensor product, this symbol is the tensor product symbol, and this symbol is also known as cron. The tensor product is also known as cron. So it is ket psi cron ket phi. This is also, if we represent the ket psi ket phi like this is again representing the tensor product. So what is the tensor product in this case? Ket psi, let's say this is ket psi. This is a single qubit system, and ket phi is a 2 qubit system. Now what will be ket psi cron ket phi? This will be given by, so this will be iota ket 0 0 0 plus 3 iota ket 0 1 0 plus 7 iota ket 0 1 1, right? Plus now for this term 7 ket 1 0 0 plus 21 ket 1 1 0 plus 49 ket 1 1 1. You can also solve this using the matrix form. That will be little lengthier, because even if you consider a larger system, for example a 10 qubit system, the matrix representation will be very difficult to solve. So therefore actually Dirac gave the notation to solve this quantum this type of mathematics, right? So using the Dirac notation, it is a very concise representation of the quantum systems, right? So that's why this is very prevalent, and we can represent the quantum systems using the Dirac notation. Now another type of representation possible is the bra notation, when you have two bras. So now you have bra psi and bra phi. So what will this be equal to? I have to let us say I have to compute bra psi bra phi, right? So this is basically equal to, again taking the tensor product. So this will be equal to 3 bra of 0 0 plus 3 iota bra of 0 1. Now for this term plus 7 bra of 1 0 plus 7 iota bra of 1 1. So this is you can again represent the matrix form using the row vectors and column vectors, and then you can further solve it. Now another type of notation possible in Dirac representation is ket bra notation. This is very important notation, and this is also known as the outer product. Now this is, you have a ket vector here and you have a bra vector here. For example, I have taken the example of ket alpha, bra beta. So ket alpha has the dimensions of m cross 1 since it is a column vector. Bra beta will have the dimensions of 1 cross n since it is a row vector. The inner dimension must be same because we have to actually multiply the two vectors, the column vector and the row vector, and we will obtain a matrix actually. So matrix size will be m cross n. Right. In quantum mechanics, the matrices are also called operators. That is actually the second postulate of quantum mechanics. I will just explain that in due course, as we go along with this lecture. So if I have to, so this is now let us say we try to solve this example. For example, we have here ket 0 0 and bra 1 0, right? If we want to calculate the outer product for this ket 0 0 bra 1 0, so how can you do this? You have this ket 0 0 which is a column vector, so this will be 1 0 0, right? And this is 4 cross 1, and you have bra 1 0, so this will be a row vector. Row vector means you will have 0 0 1 0. This is the row vector. Now you have to base this, the size of this row vector is 1 cross 4. Now if you want to multiply the two vectors, you will get a matrix of size 4 cross 4. Now outer products are also used to calculate the operators, right? So you will get this operator, and then you can apply this operator to any ket vector or any qubit. That we will see when we go along with this lecture. Now last type of notation is the bracket notation, where we will have a bra and a ket, right? For example, this is also known as the inner product. Very important representation. This representation is very important also, which is the outer product, and this is the inner product. Now this is what is there in the inner product. The inner product will have one bra and one ket. So I have put it here, bra of alpha and ket of beta. So bra of alpha is having the size of 1 cross n. Ket of beta is having, let's say, the size of m cross 1, right? So the answer to this inner product, you will get always a scalar, right? So this scalar value can be a complex number also, right? So but the answer to the inner product will be a scalar value. That we have to remember. In order to multiply, m should be equal, because I have to multiply the row vector and the column vector, and ultimately you will get the scalar output. Result will be a 1 cross 1 means a scalar value, we will get the output. Now one important fact about the inner product is that inner product is not commutative in general. For real numbers, it will not be an issue. That means the inner product between alpha and beta will be equal to inner product between beta and alpha. But in the case of complex numbers, if you have inner product between alpha and beta, so inner product between beta and alpha will be with complex conjugate. That means you have to take the complex conjugate also for obtaining the inner product between beta and alpha. Now related to this is a very important term called the Hilbert space. Now a vector space is there, right? A vector space, if it is equipped with inner product space, which is this representation which we have just now discussed, that's the inner product. Now if we include the inner product space and the vector space, so that will result into Hilbert space. So a vector space equipped with inner product space forms what is called a Hilbert space. Now this is a very simplistic definition of the Hilbert space, but at present we can take this definition to understand Hilbert space, but there will be lot more involved in the overall definition of the Hilbert space, that we will see in the due course of the lectures which are coming, right? And this is one important point which I want to mention here is about the Dirac notation. Dirac notation is basically basis independent. So it is, I mean, this is not dependent on the basis, meaning by as in the case of matrix forms, we need to be sure, we need to the size of the computations will change depending on the basis, right? If it is a 2 qubit system, a 3 qubit system, 4 qubit, 5 qubit, 10 qubit and 100 qubit, I mean that will be highly complex. But the Dirac notation gives us the basis independent and compact. So the states, the inner product and outer products are readable without writing big vectors and big matrices. That's the advantage of having Dirac notation. I will continue with the postulates of quantum mechanics in the future lectures. Thank you very much.